Before we can tell you how the telephone works, we must say a little about sound. Sound waves consist of small and rapid changes in air pressure. The number of changes per second is called the frequency of the sound. To reproduce sound, we need a diaphragm. Here, the boy is making one with a piece of tissue paper and a comb. The paper is the diaphragm, and like all diaphragms, it responds to the changes of pressure. To transmit sound, as in the telephone, we must connect two diaphragms together. Here we are using a taut string. When sound waves hit one of the diaphragms, it vibrates. The vibrations travel along the string to the other diaphragm, which reproduces the sound. This method has many obvious snags, but the basic principles apply to all telephones. In 1874, the inventor of the telephone, Alexander Graham Bell, wrote, "If I could make a current of electricity vary in intensity, precisely as during the reproduction of sound, I should be able to transmit speech telegraphically." This is a model of part of the apparatus with which Bell made his words come true. It is connected to another identical instrument by a pair of wires. Let's see how it is made and how it works. Firstly, there is a diaphragm made of parchment. It is attached to a soft iron strip mounted close to an electromagnet which has a permanent magnet core. The instrument could be used as either a microphone or as a receiver. It works by generating current from the movement of the strip in the field of the permanent magnet. No battery was needed, but the current was weak and the system could not be used to speak over long distances. In the modern telephone, we have overcome this difficulty, so let's see what changes have been made over the years. This is a diagram of a modern microphone. The first point to note is that it is powered by a battery. These two wires carry direct current from the battery and also connect the microphone to the telephone wires, or line circuit. The second point to note is that the circuit is completed through a container filled with granules of carbon. We call the instrument a carbon granule microphone. This is the diaphragm. It is made of metal and is attached to one end of the container. Now let's see what happens when a sound wave hits the diaphragm. The wave pushes the diaphragm in and compresses the granules into closer contact. This decreases the resistance and allows more current to flow. The diaphragm then falls back and the granules move apart again, increasing the resistance and reducing the current. Let's see this again. When you are speaking, these changes occur very rapidly. The result is that the resistance of the granules, and consequently the strength of the current, varies in accordance with the frequency of the sound received by the microphone. In this way, the sound waves are turned into a rapidly fluctuating current, which you see here on the meter. It may help you to think of this current as made up of two parts: the steady current from the battery, like this, and a fluctuating current due to the sound waves. It is only the fluctuating part, which we call the speech current, that carries your words along the line to the receiver. In the receiver, the current is turned back into sound waves again so that your speech can be heard. The diaphragm is attached to an iron bar, which is pivoted and mounted close to the poles of an electromagnet. The bar is called a rocking armature, and we use permanent magnetism in the electromagnet. In principle, the modern receiver is not unlike Bell's original, but it is very much more sensitive. Now let's see what happens when the speech current arrives at the receiver. Each fluctuation of the current varies the attraction of the armature, making it and the diaphragm vibrate at the same frequency, so reproducing the original sound. That is what happens when you speak to your friend on the telephone. So far, however, we have said nothing about how one telephone is connected to another. Let's look into this now. Here is a microphone. Remember, it needs direct current from a battery to make it work. Now the receiver. One might expect to connect the microphone, battery, and receiver in series, so that A can speak to B. The system works, but it is wasteful because the battery has to do more work than is really necessary. The speech current is weakened, and we cannot speak over very long distances. For this reason, we connect our telephone system in a different way. As we can work the receiver from the speech current alone, we remove the steady current by connecting the microphone through a transformer. Transformers help us connect telephones because they will pass a fluctuating current, but stop any steady current. By placing the transformer close to the microphone and using it to step up the low input voltage, we can send messages along the line at a higher voltage and therefore over greater distances. Here, to show how they are connected, we have put the microphone and receiver close together, but in reality, of course, they may be many miles apart. With this circuit, we can only speak in one direction. To speak in both directions, we could use another identical circuit like this. This method is rather wasteful, however, because there is no reason why we cannot use only one pair of wires by rearranging the connections like this. The microphone and receiver are now coupled together through the transformers at each end. We also need switches, or telephone hooks, to break the circuit and save the batteries when they are not in use. Lastly, we need bells, and they are connected so that they can be rung even though the switches are open. Current to ring the bells is supplied from the telephone exchange, which also contains all the equipment needed to connect one telephone with another. Here we have shown all the parts spread out, but in reality, apart from the battery, they are boxed together in the modern telephones with which we are familiar. We can now see what happens when a call is made. Suppose A wishes to telephone B. First of all, A must lift the handset. When he does this, the switch closes and a signal is sent to the exchange. Meanwhile, direct current flows in the microphone circuit, ready for A to speak. We are assuming that A is connected to a manual exchange. The signal stays on until the operator answers A by plugging into his number. She now plugs into line B and makes B's bell ring by moving a key. When B answers by lifting her handset, the switch closes. The bell stops ringing and the operator connects A direct to B. You can now speak to your friend.
Aldebar 7961. Hello, Joan. This is Eric. Hello, Eric. How are you?
At both telephones, direct current is energizing the microphones. The speech current is transmitted through the transformers and along the line like this.
All right, Eric. Goodbye. Goodbye.
This, then, is a simple form of circuit by which our telephones can be connected. In busy places, only one battery is used, and that is kept at the exchange. Of course, there are not just two telephones, but many hundreds, and indeed thousands, all connected to the one exchange. The operations necessary to connect one subscriber to another are performed at the telephone exchange, either manually, as we have seen, or automatically. In every case, a direct link is established between the caller and the called. Today, we can speak to people on the other side of the world almost as easily as we can to our friends around the corner. We can do so because of the fact that one diaphragm can be made to reproduce the fluctuations of another.